So this video explains another stationary series method, which is sometimes called simple exponential smoothing or sometimes just exponential smoothing. So because it's an appropriate stationary series method, the only systematic component that you found in your historical data was level. If that's the case, this is an appropriate method. The main idea here is that older data is usually less important. I want the historical data that's closest to me to have more weight than something really, really far in the past. And so this approach actually uses all historical data that you have to make the forecast, but it does it in kind of a cunning or smart way. So it doesn't seem like you're keeping track of a bunch of stuff. The equations are relatively simple, but that's because of the smartness that it's capturing. So I want to emphasize we do use all historical data. We're capturing that in our forecast, but we are giving more weight to things that happen more recently. And so you can think about this as a form of weighted moving average. So in simple moving average, we just took 1 over n. Here, instead of taking 1 over n, I'm going to get a weighted moving average. So I'm going to say I'm going to give different weights, but still take an average. And so the weights are specifically going to decline exponentially. The one closest to us, or historical data that's closest to us, will have the highest weight. And then as you get further and further away, they decline exponentially, hence the word exponential smoothing. And so again, the most recent data point gets the most weight, but we do capture all past observations, but way out, the very, very first observation gets included, but with a weight that's smaller than the one that's more recent to us. And this does require setting a smoothing constant called alpha, and this alpha value ranges from 0 to 1. All right, so how do we do this? So here are the equations. One thing I'm going to emphasize is these equations are relatively simple. The one in the blue and the ones below will give you the same answer, but they're actually two different ways of getting our forecast. So what we're basically doing is we want the new forecast to be alpha times the last period's actual demand plus 1 minus alpha times last period's forecast. That's one way to calculate simple exponential smoothing. Another way is to use the L equation, which L of t plus 1 is equal to alpha d plus 1 plus 1 minus alpha L of t. And then our forecast, remember this is a stationary series, so our forecast is just our estimate of our level. And just like we saw in moving average, I keep calculating L of t as long as I have D of t. So I can only calculate L of t if I've actually observed something. So you need the D of t associated to get your L of t. And I'm going to keep doing that until I can't calculate L of t anymore. That's where I am. I'm currently here. I've observed everything I had, and into the future, if I'm 5 periods out, 1 period out, it'll always be L of t. And we'll see this. Another thing to emphasize is the subscript. So beware of the fact that there's a t plus 1 and a t in that equation. And so please keep those in mind, and R, which we will implement, and there'll be a video about that, and other programming languages are your friend. One issue with these equations is that we need to start somewhere. And there's a lot of text on the slide, but the main idea is to get f of 1, we need f of 0, but we don't have f of 0. So how should we start? And so that's what's known as initialization. The book presents maybe using all your past historical data, taking an average, which is what's shown on the screen. What we're going to implement in R using Holtz-Winters. If you're interested in the details, I give a link there, but it basically uses a decomposition method. You can think about it kind of like a regression. So I'm going to take a regression on the past data, and then I'm going to use B of 0 as my initialization. So it's something important as you implement. We do need to initialize, and there are many, many different ways you can do that. All right, so as an example, let's take an example here. So what we are given is we have historical data, D of t, from January and till June. So we need to initialize. And so here, as just an example of initialization, I'm just going to take the average from January through June, and that's going to be my L of 0. Okay. A approach to initialization, there are many. Okay. So we have now initialized, and if you look at the equation for L of t, we now can actually go calculate L of 1, okay? Because we have D of 1 and we have L of 0, so we can do that. And just for this example, I'm going to set alpha at 0.1. We'll talk about how do you actually set alpha, but for now, I'm just going to assume we know that alpha should be 0.1 to illustrate the application of these equations. So let's do that. So how do we get our value for L of January? Well, alpha is 0.1. Our demand in January is 15 plus 0.9, 1 minus alpha times L of 0. And L of 0 was 21.833. So that is then our value. 21.15 would be L of January. You can see the similar kind of pattern. You could keep calculating L of February and so forth by applying this equation. Okay, so that's our estimate for our level, but that's not our forecast. Okay, our estimate for our level, if we need to get the forecast, we now need to use this F equation, right? So our equation for the forecast at period T plus M is equal to L of T. Okay, so for example, in January, we need to use, to get January, I'm going to use L of 0, okay? In other words, in February, I'm going to use L of January, right? For both of those, what am I doing? I'm setting M of 1. This is sometimes known as one step ahead forecast. And so what you're doing is we're just saying one step ahead, what is our forecast? Again, reminder from our previous lecture, which we talked about in moving average, you may say, okay, why the heck am I forecasting the past? Again, we need to figure out how to set our input parameter. So we need to figure out, is alpha 0.1 actually good? And in order to figure that out, we need error rates. And so why do I care about forecasting the past? Again, because we need to calculate an error rate. The only way we can calculate an error rate is to have past observed data. So you can see here we have M of 1. You could think about that continuing, right? So you would keep using M of 1. Here, in June, I would use L of May. Again, M of 1. In July, yep, I have L of June, so I'm good to go, okay? But then when you get to August, you don't have July. You don't have L of July. That is not available because demand hasn't happened in July. And so this is when you would then change to M of 2. But remember, this is a stationary method, and therefore the only estimate we have, because in the past the only systematic data we have is that it's stationary, is we have a level. So we would assume our forecast out until the future, until we observe a new piece of data point, would be 22.167. So that's how you would do this using the equations L and F that are presented here. We will also do this using R. But it's good to kind of understand what's going on. Sometimes R makes it a little too easy. So hopefully that makes sense. Another thing to note is on the previous slide, I actually presented two different ways of calculating this. So you can actually also get the forecast column directly without doing L of T by using this equation. And so one of the things I want to note, and it's maybe a good exercise for you, is you should be able to get the same forecast in two ways. And so as long as you implement the equations, they're slightly subtly different, you should get the same forecast information. Great, so hopefully now you understand how to go implement it. You could do this by hand. Again, we will have a video showing how to do this in R. But I want to give you a little bit more intuition. First of all, why is this called exponential smoothing? What is kind of going on? So I just said that this is a way of a weighted moving average. So instead of moving average, which had 1 over n, here we are still taking an average, but we're not weighting them equally. And in fact, we're weighting them using an exponential weight. And so let's just kind of break down this equation, which L of t is just alpha d of t 1 minus alpha L of t minus 1. And so you can think about, okay, this L of t minus 1, what if I just plug that back into this equation? So I plug that back into this equation, I would have L of t minus 1 is equal to alpha d t minus 1 plus 1 minus alpha t minus 1 minus 1, right? And so if you do that, I'm just plugging into what you have here. You can see that. And now I could say, well, what if I plug in L of t minus 2, right? And you could keep doing that. This is what's sometimes called a recursive equation. You would keep doing that, right? So I now, wherever there was an L of t minus 2, I explode that out and keep going. And maybe you can see there's like a pattern happening, right? And so if you just write this another way, you can get this equation. So L of t plus 1, you can see you have alpha 1 minus alpha to the n times the observed data, and then 1 minus alpha to the t L of 1, okay? So in other words, what's happening is you are exponentially declining weights to past data. But if I summed up these kind of coefficients, the sums in front of them would equal 1. So in other words, it's a fair average. It's just not weighting them 1 over n. So mathematically, that might be hard to see, but that's what graphically is going on. So if you see 0 is right now, the one that's closest to me gets the highest weight, and everything else gets exponentially decreasing weights. And so that's what this model is doing. If you would sum up the probability, so what's the probability of this, they would sum to 1. Okay, so it's a creative, kind of smart way to take an average, but not a simple average. It's a weighted average. Okay, so you may say, okay, great. What the heck does alpha do? Okay, so one thing I want to emphasize is that for any values of alpha strictly between 0 and 1, you always get this pattern of an exponential decrease in weights. So data points further away have less weight than ones closer. What does alpha do? Alpha changes how steep this is. Okay, so you could think about, if I have a certain value of alpha, I could make this one really, really steep, and then it would decline really fast. Or I could say, no, let me make it a little less drastic, right? So alpha is changing this kind of steepness. You could think about how much weight do I put on a really early one versus a late one. I want to emphasize all values of alpha between 0 and 1 have this exponential structure, but it's like, what kind of amplification do we have? So mathematically, that might be useful to see. So you can see here the most recent period, you have alpha. The second most, you have alpha 1 minus. Then you have it squared to the third to the fourth, right? So this is where the exponential smoothing idea is we're weighting them with bigger exponents. And another thing to emphasize is, remember, alpha always has to be between 0 and 1. So this value will always be between 0 and 1. So if you know from mathematics, any value between 0 and 1, if I have an exponent on it, what happens is it gets smaller, right? And so, what is the value of changing alpha is how much do you weight the first versus a further one, right? So with a small alpha 0.1, you don't have as much weighted on the first one, but again, they always decrease as you go back. But if you have an 0.5, I'm going to weight that quite a bit. And you can see, but by the time you get to the fifth, you're a really, really small, because again, these summings have to sum up to 1. So the kind of concept of alpha is actually very similar to the concept of n in smoothing in a moving average. If I have a really, really big n, I'm basically weighting them all kind of the same. Again, it gets very smoothed out. That's a similar role of what alpha plays. And so you can see, as just an example, the blue here is the actual demand. Green is alpha 0.5, and alpha 0.1 is really quite flat, right? So if you have an alpha closer to 0, it doesn't change as much. And that's because there's less difference between the first and the last. There's still more weight put on something closer, but the coefficients of those are less different. So hopefully that makes sense. Hopefully intuitively some of that makes sense. And on that, I'm going to end this slide presentation with one thought question. So Winston Churchill famously said, "The further back you can look, the further forward you are likely to see." So he was probably a fan of forecasting, right? He's saying, look to the future, look to the past, and hopefully you can see into the future, right? And so if that's his kind of mantra, how do you think a Churchill would set his forecasting parameters? Do you think he would use a moving average of 3 periods? Do you think he would use exponential smoothing with alpha equals 1? Or maybe exponential smoothing with alpha less than 1 or alpha equals to 0? So I would like you to pause, think through this, and see what you come up with. So let's walk through this. All right, so if you picked A, his quote would be, the 3 steps back you look, the further you could see in the future, right? So with 3-period moving average, he's only looking, let's say, 3 months to the past. So that's not really representing, right? He's not looking that far, just 3 years, 3 months, whatever units you want to do. So A, I would say, is not really in line with Churchill. Now, if you think about exponential smoothing uses all historical data, as long as alpha is between 0 and 1, okay? If alpha is 1, what happens? So let's just look at this equation down here. If alpha is 1, what do we have? We have 1 times d of t plus 0 times L of t minus 1. So if alpha is 1, we are only looking at the most recent demand periods, and we're ignoring everything else. So alpha equals 1 is even worse in terms of Churchill's mantra than a moving average of 3 periods. I'm only looking 1 period. So that's not good. Okay, so like that's an extreme case that you basically only care about the most recent, ignore everything else. If you look at the other extreme case of alpha equals 0, what that says is I don't care at all about the most recent, and I'm basically gonna kind of have things really, really similar, kind of 1 over n style for everything else in the past. So this would weight the past. So it would look really, really far in the past. So I would say D would fit Churchill's mantra, but it wouldn't be that interesting of a forecast. So alpha of less than 1, so C or D would be the correct answer here. If alpha is less than 1, then we do consider the most recent piece of data, and we consider it with the most weight, but we also capture everything else that we have as far back into the future. We just don't weight it as strongly. So C or D, either of those would be appropriate answers.